is closed under countable intersections. Okay. So that means that if two sets are in there, then their intersection is also in there, and you can select even a countable number of sets from the family. Then you calculate this intersection, and that would be an element of the sigma algebra. Okay. Now I'm not going to consider an example for sigma algebra here, but you can see that clearly. I mean, example 6 will be actually sigma algebra. Okay, so there I show that the set is closed under complementation. It's closed under countable unions. Okay, and of course I forgot to mention that, but a sigma algebra is not allowed to be empty. Okay, so basically, I mean, it would be empty, then it would be the case, but it's not the case. So actually, it's a non-empty family that is closed under complementation and closed under countable unions. This is actually what sigma algebra is. Okay, so maybe I add this here to that. So a non-empty family. This is what I forgot here. So I apologize. Okay, so here please make the correction: a non-empty family. Good. Okay, now you can check out example number 6. I'm not going to go through that, but in example number 6, you have actually a family which is not equal to the power set, but it's still a sigma algebra. Okay, so you can check it out. I mean, this is an example. Maybe just see example. Okay, so see example number 6. Okay. It's actually elementary, so it's not very difficult to understand. And I hope you guys you can comprehend that. Okay. Now let's continue, guys, because what we have is actually some basic properties that sigma algebras have. Okay. And I would like you to start here with there is a first theorem here, and we're going to prove this. So the intersection of countable sigma algebras is a sigma algebra. Okay. And I would like to prove that statement here. Okay. So, but basically, what is it about? So, let me just illustrate this formally. Okay. So, what does it say? Okay. So, suppose that what you have is this. So, suppose that you have the family A1, A2, A3, etc., etc., and suppose that these are sigma algebras. Okay. So, if these sets are sigma algebras, then this implies that a countable intersection, okay, the countable intersection of these sigma algebras is also a sigma algebra. Okay, so this is what the statement says. You understand? Okay, so if you have a countable number of families which are all sigma algebras, then this implies that their intersection would be also a sigma algebra. Okay, so this is what the statement is about, and I would like to show that to you. Okay, it's kind of abstract, but I hope you understand the argumentation. Now, what do I have to show? I have to show first that this, this countable thing here. Okay, so this the countable intersection of the sigma algebra is not empty. Okay. So first I show that how it's actually is not empty. So this is the first thing that I need to do. Okay, so basically we need to show that this countable intersection is not empty. Why is that? Now, as we've seen before, okay, So since actually omega, A1, A2, A3 are sigma algebras, okay? So then it would imply that actually all of them has omega as its element, okay? So here, for instance, and since A1, A2, etc., are sigma algebras, okay, so, no, damn it. Okay, so let me just rewrite it again. So since, okay, no, I missed it. So A1, something went wrong here. So A1, A2, etc., are sigma algebras. Okay, we have that actually omega is always an element, okay, in a sigma algebra. Okay, because if omega was not in there, then actually it would not be closed under complementation, and it would not be closed under unions as well. Okay, so in this case, this implies that the countable intersection of these sigma algebras, okay, cannot be empty. Okay, so that's the first thing that I need to show. Okay, is this clear? Okay, so it cannot be empty if all elements, or if all sets contain omega as its element. Okay, so if all of them contain omega as its element, then it cannot be, the intersection of them cannot be empty. Okay, because it has at least omega as its element. Okay, and that is also the case. Now, the next thing that I would show is actually closure under complementation. Okay, so closure under complementation. What does that mean? Okay, so closure under complementation. So suppose that, for instance, you have a set B, okay, and that is an element of this countable intersection of these sigma algebras. For instance, omega. Okay, so it could be omega. Okay, so it's not empty, so it has at least one element. So suppose that this is the case. Okay. Now, if that is the case, then this implies actually that B must be an element of all sigma algebras of which the countable intersection consists of. Okay, so if it's in the countable intersection of all sigma algebras, then this implies that the set is actually an element of all, okay, so all sigma algebra of which the countable intersection consists of. So you have it here for all I. Okay, so it goes from I, from 1 to whatever. Okay. So here. Okay. Is this clear? So if it's in the countable intersection, then it must be also in each and every set of which the countable intersection consists of. Now, since actually these AIs are sigma algebras, this implies that, okay, so the complement must be also an element of all sigma algebras. Okay. Now, if the complement of B is an element of all of them, that this must also imply that the complement of B must be an element of the intersection of all of them. Okay. And that means that the countable intersection of the sigma algebras is closed under complementation. You get that? Okay? Okay, so what do I show here? Or what did I show you here? Okay, so if actually something is in there, that this implies that its complement must be also in there. Okay, so the sigma algebra of the countable intersection of sigma algebras must be closed under complementation. You get that? Now I showed that also that basically that is also closed under countable unions. Okay? So, and this is what I would like you to see here. Okay, so this will be a closure under countable unions. Okay? So what do I need to show here? So suppose that you have, let's say, for instance, the sets B1, B2, etc., etc. So you have a countable number of sets, which are all elements, okay, of the countable intersection of these sigma algebras. Okay? So the only thing that I need to show here is that if these sets are in there, then the countable union must be also in there. Okay? Because in that case, the sigma algebra would be close to the countable union. Okay? You understand? So basically, I'm showing, okay, so maybe you can leave a little space here, what would be enough. So I'm going to show you later on, so that the countable union of these sets here, and I call the index k, so k goes from 1 to plus infinity, so this is the countable union, is an element of the intersection of the sigma algebras. Okay? So this is what I'm going to show. Alright? You see? Okay, so that is what closure on a countable union means. Okay? Now if these sets are in there, you can see that. Okay? So if these sets are in there, then this must imply, on the other hand, and you can check it out here, so that all these sets, Bk, all of them, must be in each and every sigma algebra here of which the countable intersection consists of. Okay, so for all k and I. Okay? Okay. Now if that's the case, then this implies actually that you have that the countable union of these sets, okay, must be also in each and every sigma algebra of which the countable intersection of the sigma algebras consists of. Okay? And why is that the case? Okay? Because otherwise these sets here, okay, so these families here, okay, these families, I'm talking about this one, okay, so these families, alright, so I'm talking about these A's, would not constitute the sigma algebra. So what is a sigma algebra? A sigma algebra is a family that is close to the complementation and close to the countable union. So if something is in there, then the countable union must be also in there. Okay, so each and every set here from this set here must be in each and every sigma algebra which the countable intersection of the sigma algebra consists of. Now if that's the case, then this implies that actually the countable union of these sets must be in each and every sigma algebra which the countable intersection of the sigma algebra consists of. Okay? And now if that's the case, alright, so this is actually an element of all of them, okay? So you can see this here, so this is an element of all of them. Then this must be also an element of the intersection of all of them, okay? That is quite obvious. So if you have something which is in all of the sets, then it must be in the intersection of them. Period. I mean, that is quite obvious. So this means that actually that the sigma algebra is also close under, the family is also close under countable unions. So since these properties are satisfied, you can conclude here that the countable intersection of sigma algebras is also a sigma algebra. Okay. Guys, now I understand this is highly abstract, right? Okay, because you cannot imagine what it would be like and whatsoever. Okay, but at least you know what closure on the countable unions means. Okay. All right. So basically, I understand. So, but this is what mathematics is about. All I can say. All right. There are no numbers, nothing. Okay. So actually, you have to check 3 things. You only have to check. I mean, if you want to check if something is a sigma algebra or not, you have to check 3 things. First, you check if it's unempty. Okay. Second, you have to check that it's closed under complementation. Third, you check that it's closed under countable unions, period. And that's the case, okay? So I don't need to imagine what it would look like, okay? It's closed under these things. It's closed under countable unions, and it's closed under complementation, period. Then it is a sigma algebra, and that's it, okay? And this is actually relatively easy to show, so that's why I would, would consider that. Okay, now the next statement, this is something that I'm not going to prove here, so this is going to be theorem 1.21, and I will come back to it later because that will be very important, and this statement is also important, so that's why I showed it here. Okay? So, and let me just add this as a final statement here, and then we can stop because I don't want to start a new topic today. Okay, so maybe you have questions or something like that. So this will be theorem 1.21. Okay, and for any family of subsets, there exists a unique smallest sigma algebra. So for any family, okay, for any family, okay, over omega, there exists such a thing as a smallest sigma algebra, okay, a unique, and I put this in quotation marks, smallest sigma algebra okay, which contains every set of the family. Okay. Now what do I mean by that? Because that is this is not obvious. Okay, so what is the smallest sigma algebra, etc., etc. Okay, and what do I mean by this? And let me just illustrate that. So first off, let's just consider a full example. Okay, so here we have, for instance, omega that consists of the elements 1, 2, and 3. And suppose that we have a family that consists of the empty set, the set, okay, the set that has 1 as its element, so this is the elementary set, and the set omega. Okay? Now, this thing is not a sigma algebra. Okay, so A is not a sigma algebra. Why is that? Because, for instance, it's not closed under complementation. Okay? Because, okay, A is not closed under complementation, for instance. Why is that? I mean, you can see this here clearly. So, for instance, the complement of this set here, of this elementary set, is actually equal to the set 2 and 3, right? You see? Okay. And the set that consists of 2 and 3 is not an element of the family. You see? Okay, it's not in there. So it's not close under complementation because there is at least one set of which the complement is not included into the set. Okay? But this statement says that this sigma algebra, or this family here, but it's still a family, right? This family can be extended in such a way that there is a sigma algebra. Okay, so it can be generated, to a sigma algebra. So the statement, okay, so theorem 1.21 says, okay, let me just illustrate that. So theorem 1.21 says that first that this family can be extended, okay, so I put this in quotation marks, to a sigma algebra. Okay? And for instance, if we could extend this to be, let's say, for instance, to be as a power set, okay, so the power set would be also sigma algebra, okay, but the power set is not the smallest sigma algebra, okay, so let's say, for instance, okay, example to the power set, okay. Okay, you see? So for instance, I could put, more sets in there. I mean, this has 3 elements, and the power set would have 8 elements, so I could include these missing elements, all right? And then I would get the power set, and the power set would be also actually the sigma algebra, okay? All right? That is always the case, so the power set is always a sigma algebra, no matter what. But the power set is not the smallest sigma algebra in general, okay? Because there might be exist in another set for which the cardinality is then less than that of the power set, okay, which is smaller than the power set in that sense, but would still constitute the sigma algebra. Yes.
But regarding this example, we cannot find a set that is not a power set but also close under complementation, or is there an example?
There is. So for instance, okay, so I could extend this to be the power set. That would be a possibility, and then the power set would be actually a sigma algebra, and the power set has actually all elements of the family in there. So this is what the theorem says. Okay, so basically I could extend that in such a way that, you know, a sigma algebra is generated. Okay, all right, and that sigma algebra has all elements from the family, but the power set is not the smallest in general. Okay, so but the power set is not the smallest sigma algebra over omega. In general, that contains, okay, that contains all elements of the family. Okay, you understand? Okay, so I'm going to give you the smallest sigma algebra, okay, that contains all elements of the family, which is not the power set. Okay, so the power set would be, all right, obviously a sigma algebra, but it's not the smallest one. And the smallest sigma algebra that contains the smallest sigma algebra that contains okay, the elements of the family is the following. Okay, so leave a little space here because I would like to call it somehow. So that would be consisting of the empty set, the set that has 1 as its elements, okay, then namely 2 and 3, okay, and omega. Okay, so because you can, as you can see this here, so these elements here, okay, that I could put more emphasis on, okay, these were elements of the family. You understand? Okay, but the family was not a sigma algebra, and now I extended it in such a way that a sigma algebra is generated. Okay. Okay, and among those sigma algebras that contain all elements of the family, there is actually one which is the smallest. Okay? And in that case, that would be actually the intersection of these sigma algebras that contain all elements of the family. Now this is what I'm talking about. So these are the elements of the family here. Okay? So the blue ones, all right? So these are the elements of the family. Okay? And actually there is no sigma algebra. This is a sigma algebra, of course, because it's closed under complementation, guys. Okay? It's closed under complementation, so if something is in there, then its complement must be also in there, right? And if 2 sets are in there, then the union must be also in there. And since actually the set omega is finite, then this implies that it's also closed under countable unions. Okay, so a countable union. Let's say if countable sets are in there, then the countable union must be also in there. So this set is a sigma algebra, and this is the smallest sigma algebra. And this is the smallest sigma algebra generated by the family. Okay, so we call this, and I call it sigma of A. All right, so this is the name of it. So this is the sigma algebra, the smallest sigma algebra generated by the family A. Okay. generated by the family A. Okay, so as I mentioned before, A was not a sigma algebra, okay, because it was not closed under complementation. Okay, and theorem 1.21 says, no, sorry, this is theorem 2.21. No, not 1.21. This is theorem 2.21. Okay, I messed it up. 2.21 in election notes. Okay, so this theorem says that there is always a possibility for that. Okay, so if you have a family which is not a sigma algebra, that can be extended in such a way that what you're going to get is a sigma algebra, and among those sigma algebras that has all elements of the family, actually the countable intersection will be the smallest one, as we shown here in the previous one. Okay, so that is the smallest sigma algebra which is generated by the family. Okay, all right.
Which makes sense.
Yes. The intersection of the sigma algebras that contain all elements of the family will be the smallest sigma algebra, okay, that is generated by the family. And this is what the theory says. Okay? Okay, so the intersection of all sigma algebras that contain the elements of the family will be the smallest sigma algebra generated by the family. And this is what I said. So a sigma algebra generated by the family is actually a sigma algebra that contains all elements of the family. As I said here, this was, okay, so the family was not closed under complementation, so it was not a sigma algebra, but it can be extended to the intersection. Okay, and among those possibilities, you take the smallest, and that is, I mean, this is what the theory is about. You understand? Okay. Now, guys, I would like to stop here. And if you have questions, just don't hesitate to ask, okay? Just one announcement. I'm going to publish assignment 2 on Sunday. Okay, so Sunday evening, assignment 2 will be out. And the deadline will be also Friday. And please do not forget that the deadline, the first assignment is today. Okay, so at midnight, so please send me an email by midnight, okay? If you miss 1 minute or 2 minutes, okay, I will consider that. Okay, so I will wake up on Saturday and check my emails at 7 a.m. So it should be in there. Okay, but if I don't, then sorry. Okay, all right. Okay, guys, but just for you to know. All right. See you next Wednesday.